The third gas law is Gay-Lussac's law. He was another Frenchman, and what he observed was a relationship between temperature and pressure. So I'm going to give you a few seconds to turn off your video to copy down these notes. And here's the problem we're going to work on. Okay, so you saw in the demonstration videos that as the temperature decreased, so the one professor put that ball, that metal ball filled with a gas attached to a pressure gauge into liquid nitrogen, and you saw the pressure go down. He then put that same metal ball attached to a pressure gauge over a flame, and you saw the pressure increase. And that is Gay-Lussac's law right there. Pressure is directly proportional to temperature in kelvins for a fixed mass of gas held in a constant volume. So if temperature goes up, pressure is going to go up. If temperature goes down, pressure is going to go down. And we see that happen in car tires. This is the classic example for Gay-Lussac's law. With a car tire, you do not want to overinflate your car tires, because what happens is if you overinflate them when they are cool, you drive down the road, there's friction with the road, that increases the temperature of the tires, and that will increase the pressure. And so then they could have too much air in them and too high of pressure, and you have a problem. Also, you will see this if there are drastic temperature changes outside. You might notice in the winter, even though your tires were perfectly fine during the summer, that all of a sudden you have to put some air in them to increase the pressure, because what happened is the temperature is lower and the pressure went down in them, so you need more air. And likewise, maybe your tires were fine for the winter, but all of a sudden you realize that there's too much pressure in them during the summer. Well, that's because during the winter you needed more air. You have to let some air out during the summer because temperature increased, so the pressure increased. So you have to lower the pressure by letting out some air. You also saw in the other demonstration with the candles that, and I do want to fix part of the explanation in that. I really do not like what they said about the air pressure, about the water being pulled into the beaker. The water is not pulled into the beaker, it is actually pushed into the beaker. I'll talk about that in a minute. With the candle demonstration, when they heated it up, you didn't see that so much, that the pressure was increased and the water was pushed down. But when the candles went out and all of a sudden the temperature was lowered, the pressure decreased as well. And so the atmospheric pressure being higher than the pressure inside of the beaker actually pushes the water down and into the beaker. It's not being pulled, it's actually being pushed, because air always wants to go from high pressure to low pressure. And so that is what was happening with the demonstration with the candle. So this, like Charles' law, is a direct relationship. If temperature goes up, pressure goes up. We can write that the same way, P over T equals K, and the same stands true. If K is 1, P and T are 1, 1 over 1 equals 1. If I increase the pressure to 2, I have to increase the temperature 2 times, so 2 over 2 is still 1, and so on and so forth. So we can actually write this relationship, since the constant is the same, and we can compare two different situations. So let's take a look at the problem. And this is a tire pressure problem. Before Molly began a car trip, she measured the air pressure in her car tires and found that it was 32 psi at 18 degrees Celsius. After 2 hours of driving, she found that the pressure had increased to 34 psi. What was the new temperature of the air in her tires? So the first thing we have to do is we have to highlight what we know. These are the values we are given, and we want to find temperature. So P1 is 32 psi. T1 is 18 degrees Celsius, but we have to convert this to Kelvin. The reason for these conversions, I should have told you that in the last video, is because when we're doing this math, we don't want to deal with negative numbers. The Kelvin temperatures get rid of negative numbers. If we had negative numbers in these calculations, they would not work properly. So that is the reason for converting to Kelvin. So when I add these two numbers together, I get 291 K. P2, T2. My second pressure is 34 psi, and I want to know the temperature. Now it looks like I'm going to run out of room, but we can fix that. Okay, so my equation is, I'm going to do that on this other sheet of paper here, so I have plenty of room. P1 over T1 equals P2 over T2. I made a mistake up here. This should be T2. Sorry, I was getting my laws confused. Okay, so when I plug my numbers in, I put 32 psi over 291 Kelvin, 34 psi over T2. Now the easiest way to solve this equation is to cross multiply since I have a proportion. So I'm going to say that T2 times 32 psi equals 291 Kelvin times 34 psi. T2 equals, I'm going to divide both sides by 32 to get T2 by itself, so 32 psi divided by 32 psi equals 291 K. Those cancel, so T2 equals, now 291, gotta put this into my calculator, times 34 is 9,894 divided by 32. And I get a value of 309. Now, if I go back up here, though, I only have two significant digits, so I cannot write 309. I have to round that to 310 so that I only have two significant digits. The 0 is not significant because there's no decimal point after it. Okay, so what I want to do next is take a look at page 257, questions 1, 2, and 5. So take a minute to get out your book, take a look at those, try to answer them yourself, and then I will go over the answer for you. Now, the number 1 requires graph paper. And so I did put a link on my teacher page and grade link for graph paper that you can print off. It's the graph paper that I am going to use to show you the problem. So if you need graph paper, go ahead and print that off if you need it. Otherwise, you can, if you have graph paper from math, that's fine to use that. Okay, so page 257, question number 1. It says, look at table 10.2 again. After converting all the temperatures to kelvins, graph these values with temperature on the x-axis and volume on the y-axis. And so I did that. Here is my graph, and you know what? I cheated a little bit. I didn't have to convert those temperatures. They did it for me on the same page in table 10.3. So I just used those values. Maybe you realize that. And so when I plotted those, temperature here, volume here, I get this nice graph here. And so the first question, A, says, what is the slope of the graph? So I'm going to show you the answers to that. So you can check your answers. Or excuse me, it's not the slope, it's what is the shape of the graph. When I look at my graph is a nice straight line. For B, they ask me, what is the slope of the graph? Well, I found that by rise over run, change in y over change in x, and I just picked 2 of my points. I picked 1,500 and 400 and 200, subtracted this 500 over 200 and got 2.5. And so the slope of my graph, they said if we put Charles' law into slope-intercept form, is V equals KT. This is my slope. So my slope is the value of K, which is 2.5. For C, if the temperature is in kelvins, what is the y-intercept of the graph? What significance does this have? Well, right here, I extend my line and it hits 0. The significance of that is that it is 0 Kelvin. That's not okay, that's 0 K. This corresponds to absolute 0 when the volume of the gas goes to 0. So that is the answer to that. I'm going to go ahead and show you the answers to 2 and 5. I should have done that at the beginning. So there you go. For question number 2, it says, what do you think the graph of pressure versus volume would look like and the graph for temperature versus pressure? I actually gave those to you in your notes. Pressure and volume is an inverse relationship, goes down. Pressure and temperature, direct relationship, goes up just like volume and temperature. And then for number 5, I will go through the steps here with you. The question says, a gas has a volume of 111 milliliters at a temperature of 32 degrees Celsius. What volume will the gas occupy at standard temperature if pressure is held constant? So, I look for my V1 and my T1 that I have. This is volume and temperature. My initial volume is 111 milliliters. My initial temperature is 32 degrees Celsius, but I have to convert that to Kelvin. So I add 273, and that is 305 Kelvin. I'm looking for my volume, and my T2, my final temperature, it says standard temperature. So standard temperature, remember, is 273 Kelvin. So I plug this into my equation. V1 over T1 equals V2 over T2. plug my numbers in. 111 milliliters over 305K equals V2 over 273K. This is where I do my cross multiplication to get my answer. Or actually, I'm not going to cross multiply. I'm going to multiply by 273. It will be shorter, fewer steps in the long run. So multiply each side by 273 Kelvin. I could also cross multiply. It just takes more steps. So if you choose to do that, you can do that as well. So V2 equals 30,303 milliliters divided by 305, which is 99.4 milliliters. Now, I'm looking for 3 significant digits up here. Not 2. The temperature, because remember when you add these numbers, that will increase this actually because of the rules for addition to 3 significant digits. So that is fine. It's not 2, it actually is 3 significant digits. Okay, so because I still have quite a bit of time left here, well, I'm going to do another video for the homework because it's easier for me to upload shorter videos. So I'm going to do another video for the homework. So be looking for the homework in the last video that I'm going to do for today.